Welcome to this essential guide on Westgard rules and quality control in the clinical laboratory. We will explore how these rules catch dangerous analytical errors while avoiding the trap of false rejections. Quality control is a patient safety mechanism, not just a compliance checkbox. High-quality QC resolves the cost-quality paradox by maximizing error detection and minimizing false rejections. This reduces expensive repeat testing and protects patient safety. Westgard rules assume that random errors follow a Gaussian or normal distribution. Key metrics are the mean, standard deviation or SD, and the CV. Remember that in a stable system, 5% of results fall outside 2SD and 0.3% fall outside 3SD by chance. The Levey-Jennings chart converts statistics into a visual narrative of instrument health. It uses warning limits at plus or minus 2SD and control limits at plus or minus 3SD. The chart helps distinguish between random scatter, shifts, and gradual trends. Using a single rule can lead to failure. The 2SD rule has high false rejection, and the 3SD rule has poor error detection. The Westgard multirule solution combines rules to optimize the balance, using a warning rule as a gatekeeper. The 1 to 2S violation acts as a yellow light. Slow down and check, but do not reject the run. If the warning is triggered, we check the rejection loop rules: 1 minus 3s, 2 minus 2s, R4s, 4 minus 1s, and 10x. If any rejection rule is violated, reject the run. Random errors are unpredictable, sudden fluctuations, often transient glitches. The 1 to 3S rule catches a single point beyond 3SD, and the R4s rule checks the range between 2 points exceeding 4SD. Causes include bubbles or pipetting errors. Systematic errors are constant biases or gradual drifts. The 2 to 2S rule detects 2 consecutive measurements exceeding the same 2SD limit. The 4 minus 1s rule catches smaller biases with 4 consecutive points exceeding the same 1SD limit. Causes include calibration drift or reagent degradation. The 10x rule detects invisible drift, where 10 consecutive points fall on the same side of the mean, even if they are within 2 SD limits. This small bias can shift the reference range for chronically ill patients. Common causes are subtle calibration bias or long-term instrument drift. Reliable QC depends on reliable baseline statistics. Collect at least 20 measurements over 10 days and exclude outliers. Use minimum 2 control levels and determine QC frequency based on risk. Your Westgard rules are only as good as the statistics behind them. The golden rule is not to just repeat the control hoping it passes. First, classify the error as random or systematic. Then, investigate the root cause using methods like the fishbone diagram or the 5 whys technique. Finally, fix, verify, and document the corrective action. Case studies demonstrate theory in practice. A 2 minus 2s violation was a systematic electrolyte shift caused by a faulty calibrator lot. A 1 minus 3s/R4s random violation was caused by construction vibrations. A 10x systematic drift was caused by copper leaching interference. Customize your QC rules using the sigma metric, which measures process capability. High sigma processes, greater than 6, require simpler QC, like 1 minus 3s only. Low sigma processes, less than 3, require stricter multi-rule QC and higher frequency to ensure safety. The future of QC is continuous, data-driven, and proactive. This includes patient-based QC using moving averages and AI and predictive analytics to anticipate failures. Total quality management integrates pre-analytical and post-analytical checks. The measure of a QC system is its ability to ensure every patient result is accurate. Key competencies include balancing false rejection and error detection, never treating a 1 minus 2s warning as a rejection, and troubleshooting the root cause. Quality is a habit.